What's up, folks? So over the last month, I've been reading and learning about transformers. So I read a bunch of research papers. I started implementing the original transformer paper from scratch just a week ago. So I thought, well, it's still fresh in my memory, I should go ahead and do a small deep dive into the Attention is All You Need paper. So without further ado, let's jump into it. So let me open the paper. Attention is All You Need. So actually, before I go and do a high-level overview of this paper, I'd strongly recommend you go and read these three blogs, which I already briefly mentioned in my previous video, which I'll link somewhere here. So it's from Jay Elmer, and they are super useful if you're new to transformers and to attention mechanisms and stuff like that. So this one is really nice, introduces you to the concept of word to vec, to like word embeddings in general, and then there is this sec-to-sec tutorial, which is also really nice. And finally, the most relevant one is this illustrated transformer, which is really nice. So take your time, read through those, and then you'll have the required prerequisite knowledge for understanding this video. Although you can try and do it without reading the blogs. I just strongly recommend you go through the blogs. Also, so yeah, I already said this. So like a week ago, I started implementing the original transformer paper, and you can see it here in my coding history. So hopefully all of those nitty-gritty details will be like fresh in my RAM. So without further ado, let's jump into the paper. Okay, so let's first do a short high-level overview of the whole paper. So in 2017, a team from Google published this paper called Attention is All You Need. And they basically introduced this novel architecture called the transformer. The main idea there was that they stopped using RNNs and CNNs and instead used this simple architecture, but they used attention in a really clever way. That enabled them to have models, transformers, which are much more parallelizable and thus more compute optimal than previous architectures. And they basically show here that they basically say, hey, this is better than LSTMs and better than GRUs in modeling long-range dependencies among words, and also much more compute optimal. You can see the architecture here, and how it functions on the high level is you basically take the input sentence, you convert it into embeddings, you add something called positional encodings, which I'll show you right now because I've been coding that up from scratch on my own. So here's my implementation, and just visualize it because it helped me also understand better how these look like. And what you basically see here is that every single row is something that gets added to the token representation. And using this information, the model knows where all of the tokens came from. Otherwise, the word order would get lost. So this is really important. And they didn't use the learned representation for this positional encodings. They just use this. These are basically sine and cosine functions whose frequencies form a geometric progression. And it turned out to be as good as a learnable positional encodings, which they showed in ablation studies later in the paper. Okay, enough of that. Let me go back to the paper. So then what you do is you pass those representations into multi-head attention, which I'll go into a bit more depth a bit later. And they then apply something called pointwise feed-forward network. Finally, the output encoder representations are fed into the decoder, which is super similar to encoder part, except that it has this middle multi-head attention, which actually attends also to encoder representations and not only to previous representations from the same stack. So that's the difference. And this bottom multi-head attention also uses something called like masking. Basically, the current token can only see representations that came before it, and that makes sense because transformer was used to do some machine translation, so translating from English to German and English to French, and thus it doesn't make any sense to see the like future words because you're trying to predict the future words. That's why the mask is used. And I can show you that here. just a second. So this is how the mask looks like. You basically put some really big negative numbers into before the softmax in the attention module, and that causes masking of token representations. Okay, so that was a brief overview of the architecture. Finally, you have the linear layer and softmax, which creates a distribution, and you're just trying to minimize the distribution, either using cross-entropy loss or KL divergence in the case of soft labeling, which I'll explain a bit later. And hopefully, I know this probably sounds gibberish at the moment, but just stick with me and you'll get to kind of slowly learn all of those details in time. Okay. So attention, I already mentioned it. They are using something called scaled dot product attention. I'll explain that a bit later. And pointwise feed-forward networks, I mentioned those. So basically what they do is you have a single network, and it processes a single token representation. And that's it. You just you just train a single network, and you just do something like a for loop over all of the token representations. Embeddings and softmax, positional encoding, I showed you how this looks like. So basically they use these sine and cosine functions with frequencies which form geometric progression. And then they argue why self-attention is good. So why it's good is it's computationally really nice thing. So basically, if you compare the second row recurrent network with self-attention, you have that the maximum path length is O of 1 for transformer, whereas it's O of n for RNNs, and similarly complexity of a layer is n to the n squared times d, where n is the number of input tokens, which is usually smaller than d, which is the dimension of the model, which was 512 in the baseline model. So that's why it's so basically attention plus highly parallelizable. That's what's the secret sauce of transformers. Okay, they then they trained this model for translation tasks, as I already mentioned, and they achieved SOTAs, so state of the art, on both English to German and English to French translation tasks. They also use some really interesting optimizing learning rate schedule, and I can show you that briefly in this super nice blog called the let me see if I can find it, the annotated transformer, and I'll link the link down in the description. So basically this is how it looks like. You basically you linearly increase the learning rate initially for the warm-up number of steps, and then you start decaying them proportionally to this inverse square root of the number of steps. So that's how the learning rate schedule looks like for their transformer, and they use a simple like a pretty popular optimizer, like first order optimizer called Atom. Finally, they did some regularizations, dropouts, label smoothing, which simply said you usually want to match like a one hot vector. What label smoothing does is, instead of putting 1 on the like ground truth word, you put 0.9, and you just spread out the rest of the mass across the rest of the vocabulary, and that's it in a nutshell. So I mentioned machine translation. They did a ablation study. This part is interesting. So they figured out that bigger models are better. And like fast forward to 2020, you know this, and you have GPT family of models where GPT-3 has 175 billion parameters, and you have BERT and BERT derivatives, and all of those models are huge compared to this one. I think it was the original transformer had around 100 million parameters. So compare that to 175 billion today in 2020. And finally, they conclude saying they have ideas of using this same architecture also in vision and speech recognition. And again, fast forward to 2020, you have this visual transformer which performs really good, really nice with images, and that's super exciting. Although only in the big data regime, but still. Finally, they have some nice visualizations here showing how different multi-head attention modules attend different words in the previous layers. So you can see here that the masking, this word masking, making, is focusing a lot on more difficult, which makes sense if you look at this semantically. And yeah, there are just nice, interesting emerging patterns that that appear when you train these transformers networks. So with that being said, let's go a bit into more depth about how the multi-head attention actually works. Okay, let me try to explain how multi-head attention works, and I'll use two methods here. I'll first use JLMR's visualizations because they're really nice, and I'll use my own code I've been developing over the last couple of days. So let's see how it works. So basically, you have so let me open the paper. We said you convert the sentence into a sequence of embeddings, right? And you're basically here. And now let me show you how the multi-head attention works. So these are the embeddings. So you have, say, thinking machines, and in real world, you won't actually have a single vector for a single word. There is something called tokenization, and concretely, transformer use something called byte pair encoding, meaning thinking will actually be split maybe into two vectors, like one which actually corresponds to THIN, I don't know, or and the second one for the KI, and the third one for NG, whatever. So, but basically at the end you have a sequence of vectors. And what you do now is you apply three neural networks. One will produce something called queries, the second one will produce something called keys, and the third one will produce values. And now you basically will use the same network for every single token vector to produce queries. So there are only three networks in one multi-head attention, and there is one more like at the output, but I'll mention that one a bit later. So what you do now is you want to find how similar query from a particular word, say query 1, is similar to keys of every single token in a sentence. So you do a dot product. So that's more generally called a scoring function, but the transformer paper used something called scale dot product scoring function. So you do a dot product between query 1 and key 1, and you get a number, say 14. And then you do a dot product between query 1 and key 2, and you get 12. And those are scores. And now you do softmax, which makes the sum goes to 1, and you get 0.88 and 0.12. And basically, you take those numbers, you multiply the value vectors, value 1, value 2, and Jay nicely visualized it here. So because this is 0.12, basically this one will be dimmer, and then you sum them up and you get Z1. So that's how the attention works. But now the only difference with multi-head attention is basically you split this query 1. In the baseline transform model, it has 512 dimensions. Once you split them into 8 heads, that's the number I used in the paper, you get, so one query 1 will actually have 64 dimensions. And then you do the same procedure I just described, but independently for all of those 8 heads. And once you get Z1s for all of those 8 heads, you just concatenate them together, and you do another feed forward through a neural network, and you get the final result. And that's when you get to this part here, before addition with this residual connection. So that's how it works in a nutshell. Now, I mentioned the scoring functions, I mentioned dot product. Why do you do a dot product between query 1 and V1 and V2, whatever? The reason is that gives you a similarity between those vectors. So what I mean by that, let me use Google for this. So this is a 2D case. So basically, I told you, so those vectors are like, so query 1 and key 1 or key 2, they have 512 dimensions. But if you kind of maybe project them into 2 dimensions, and you get something like this. And now the smaller the angle, the more similar the vectors are. And basically, if so the smaller the angle, you'll get higher score here, and basically that means you'll attend more to that particular representation. So I hope this didn't confuse you too much, because that wasn't the point. But yeah, let me know if this helped or it did not. Just reiterating once more, you take queries and you take keys, and you want to see how similar they are, and if certain query is really similar to a certain key, then you want to take into account that vector with a high score. And basically, if vectors are orthogonal, the score will be 0. If vectors are like even on the opposite side, then you'll have a negative score. So that's basic cosine distance, basically. Jumping into code, I want to show you how it looks like in Flash. So as I said here, so you have these query, key, and value nets. You apply them separately on all of those tokens, and you get query, key, and value batches. And once you do that, you pass that into the attention. You pass that into the attention function, which does some matrix multiplication, and that way you basically apply attention to all of the tokens and through all of the batches in a really optimal way. But it's harder to understand than by looking at single batch and examples that I showed you in the blog. Then we have potentially some masking operation, and as I mentioned, in case you want to ignore a certain representation, you just put negative infinity. Oops, this should be negative here. It's still a prototype code, so forgive me for this. And then you apply softmax to scoring functions. You get the attention weights, and also one more detail is that you sometimes want to drop certain attention weights, which means certain attention weight will get pulled to 0. And that's one more nitty-gritty detail of implementation. And then you do once more matrix multiplication between attention weights and between those values. And here is where you get those. Let me just open this up. These vectors. And now you want to concatenate them and do one more pass through a neural network to get the final result. And that's exactly what I do here. So intermediate representations, and then we change the view of those, and finally we do another projection, and you get the final results. So I hope this wasn't too hard to follow along. If it was, please let me know in the comments, and I'll be open sourcing this code in a week or two, so you'll be able to go through the code at your own pace and read through the blogs at your own pace. So hopefully all of this together will help you grasp how all of this works and fits together. Finally, I just want to give you a feeling of how the actual machine translation training for the original transformer looked like. So you basically have two corpuses of text. You have, say, German and you have English. And those corpuses are synced, meaning you have one sentence in German and there is a corresponding sentence in English. So for example, wissen Sie, eines der großen Vergnügen beim Reisen und eine der Freuden bei der ethnografischen Forschung ist, gemeinsam mit den Menschen zu leben, die sich noch an die alten Tagen erinnern können. That was a bit of German for you. And you basically have a corresponding sentence like here on the other side of the document. If I open it up, you know, one of the intense pleasures of travel, blah, blah, blah. So having those two synced, so basically, if you're translating from English to German, the German sentence is something called like the gold translation. So somebody like a professional translator translated the sentence. Okay, so once we have those two sentences that correspond to each other, what you do is the following. So you have the transformer, you take the English sentence, you tokenize it, you embed it, you do a forward pass through the encoder module here, and you get representations. On the other side, you take a German sentence, you again tokenize it, but now what you do is you put as a prefix, you put this start of sentence token. So that's here, and then you do forward pass here, and finally the gold translation. Just you convert that into soft labeled distributions, and you just do KL divergence, and then doing backprop will train and tune the weights of the whole transformer model, and that's a single training step. The important part is that you want to use those masks so that a certain token, like say a token that's here, cannot see tokens that are coming afterwards. That being said, if you found this video useful, consider subscribing to this channel and hit that bell icon to get notified when I upload a new video. And until next time, keep learning deep.